Okay, so let me also start off by thanking the organizers for giving me this opportunity to disseminate my research to such a broad audience. So I'm going to tell you about statistical mechanics of the fractional quantum Hall effect. And this is the first work that I ever did in this field, so I've decided to pick that up and tell you about it. Okay, so the plan of the talk is as follows. I'm going to first give you a very quick introduction to what are called integers and fractional quantum Hall effect. And then I'll tell you how you can understand the fractional quantum Hall effect in terms of what are some exotic objects called composite fermions. And then I'll come to the main part of the talk, which is building up the spectrum of fractional quantum Hall using these composite fermions. Okay. So experimentally, the integer quantum Hall effect was discovered by Klaus von Klitzing. So probably all of you know what the Hall effect is. You take a sample, you put it in a perpendicular magnetic field, you run the current one way, and you measure the voltage in the opposite direction. So what Klitzing did was take a two-dimensional system of electrons, placed it in a strong perpendicular magnetic field, ran the current this way, and measured the voltage this way. So this ratio of the transverse voltage to the longitudinal current is what is called the Hall resistance. And what he found was this Hall resistance was exquisitely quantized in some fundamental units. H is the Planck's constant, E is the charge of the electron. And this quantization is as exact as we can measure. So it's just limited by instrument capabilities. And this effect is independent of of details of the system. So whether you take systems as different as like transistors or graphene or gallium arsenide, they all produce the same effect. It does not depend on things like what is the sample geometry, what kind of impurities you have in the system. So it's quantization in a macroscopic system. So this sample can be like centimeters long and you still see this quantization. So how do we understand the integer quantum Hall effect? So if you don't have any magnetic field, then electrons just pile up and fill up what is called a Fermi liquid. So you just put electrons and just depending on their density, they fill up to some number of states. But in the presence of a magnetic field, this spectrum splits into highly degenerate bands called Landau levels. So each of these levels has many degenerate states. And whenever you fill an integer number of these levels, you get a gap to the system. And the gap is what is crucial to the quantum Hall effect. So whenever you have a gap state, you get quantization in this system. And here the gap is set by what is called the cyclotron frequency, and this frequency is just proportional to the magnetic field. So if you go to higher and higher magnetic fields, you can increase the gap and you get better and better quantization. So one nice thing about why this shows quantized transport can be understood using semi-classical physics. So as you all know, in the presence of a magnetic field, you have this thing called the Lorentz force, where if you have a charged particle and you put it in a perpendicular magnetic field, it goes in closed loops. So in the bulk of the system, these loops are closed, so they don't carry any transport. But if you look at the edge of the system, then you have these skipping orbits. And because the direction of these orbits is just fixed by the charge of the system and the magnetic field, these orbits cannot actually backscatter, because once the direction is fixed, the orbits can just move in one direction. And if you place some disorder or anything, then it just skips that and goes around, right? There is no way for this to backscatter, go back, because the direction of the magnetic field fixes this. So that's why this effect is very robust to things like disorder. So very soon after Klitzing's discovery, Sui, Stormer, and Gossard made better samples, went to larger magnetic fields, and did essentially the same experiment. But what they observed was this Hall resistance was quantized to units of 1/3 E square. So Sui seems to have remarked that he found quarks in a condensed matter system, and somebody told him that one should be very careful about capital M and small m. This is all a milli-electron volt phenomena, and quarks only come up in mega electron volt or higher energies. So quarks are not at all relevant to this at all. So this is the question that one is trying to understand. Why is it that you suddenly get some fractionally quantized Hall resistance? So fractional quantum Hall effect turns out to be an extremely difficult problem. So for a theorist like me, there is a nice limit in which you can describe the problem, where what you can do is you set the cyclotron frequency to infinity. So all the physics is happening only in the lowest Landau level. And this Landau level is now partially filled. So here is an example of filling factor 2/5. So you have 10 states in the lowest Landau level, and 4 of the electrons occupy these states. So in general, if you have no interactions between the electrons, then this is a highly degenerate manifold, right? You have 10 choose 4 ways of filling 4 particles in 10 orbitals. But there are always interactions between electrons, because electrons are charged particles, and charged particles interact via Coulomb forces. So in this highly degenerate manifold, once you have Coulomb forces into account, you get a unique gapped state. So that is how you get fractional quantum Hall effect. That's what produces the gap. The Coulomb interaction somehow from this highly degenerate manifold picks a unique state. But we don't even know how to solve 3 particles interacting with each other. So what hope do we have of solving like an Avogadro number of particles interacting with each other? So progress in the field of fractional quantum Hall effect essentially comes from this old age Greek way of doing things, where you essentially try and guess an answer and then check whether that answer gives you a nice representation of the actual Coulomb problem. So the first step in that direction was made by Laughlin, who essentially just proposed what the answer for 1/3 should be. So he proposed this Jastrow correlated wave function. So Z is the complex representation of the 2-dimensional coordinate. And what Laughlin proposed was that you take a wave function which is of this form, Zi minus Zj to the power m. So what this wave function does is if you bring 2 particles close together, then this wave function vanishes very quickly. So if the wave function vanishes, then what you get is lower Coulomb penalty for this. So if the wave function vanishes as quickly as you can make it vanish, then the Coulomb interaction energy is low. So that's a good way to form a ground state. Moreover, he actually showed that if you look at this state, and if you look at excitations of this state, so this is the ground state, now you go and look at excitations of this state, then this is actually a fluid that carries fractionally charged particles. So this is an amazing thing that happens in condensed matter physics, where you have electrons as the fundamental particles, but certain emergent particles come up which have no relevance at all to the electrons. So you get like E/3 particles in this system, where you only have electrons to begin with. So somehow magically things rearrange in such a way that you get emergent particles with fractional quantum numbers. So very soon after Sui, Stormer and Gossard's discovery, better samples were made, and there were like a whole zoo of fractions which were observed. And these go along this n/2n plus minus 1 sequence. So primarily you get states which are like 1/3, 2/5, 3/7, 4/9. So they all fit along this sequence. So one can ask, why is it that this sequence is particularly picked out? So actually one interesting thing to note is that if I actually remove the numbers from this plot, you cannot tell me which of these plateaus corresponds to integers and which corresponds to fractions. So phenomenologically, the integer and fractional Hall effects look very similar. So my advisor ended up asking this question of, can we unify these two together? So can the fractional quantum Hall effect be understood as the integer quantum Hall effect of certain emergent particles? And the answer turns out to be yes, in terms of what are called composite fermions. So composite fermions are electrons bound to 2 flux quanta or 2 vortices. So you have a system of electrons in a large magnetic field. From this large magnetic field, 2 fluxes go and bind to each of these electrons to form composite fermions. And these composite fermions, to the 0th order approximations, are non-interacting particles. So they don't talk to each other. And just like non-interacting particles in a magnetic field form Landau levels, these composite fermions themselves form Landau-like levels. And whenever an integer number of these levels are filled, you get fractional quantum Hall effect. So you can then work out the numbers and show that whenever n nu star is n, this is the number of filled lambda levels of composite fermions. And whenever that number is an integer, you get fractional quantum Hall states of electrons. So that's particularly why this n/2pn plus minus 1 sequence is picked out. Okay, so in terms of pictures, what do the states look like? So filling factor 1 of composite fermions corresponds to filling factor 1/3, and this actually turns out to be the same state as what Laughlin had described. This Jastrow correlated wave function that I had shown was actually the same. So filling factor 2 corresponds to 2/5, filling factor 3 corresponds to 3/7, and this is the main n/2n plus 1 sequence that you saw. And not just the ground states, you can also describe things like excitations very easily, right? If you want to say what is like a missing particle, that's like a missing hole in an otherwise filled level. Then there is an extra particle, and you can get neutral excitations by putting these two together. Again, this is the way to now go ahead and build a spectrum. So if you just brute force exact diagonalize the problem, so let's say I take some finite number of electrons, put the system on a computer, and then just minimize the Coulomb energy, then I get a spectrum which looks like this. So now how do we go about understanding the spectrum using the composite fermion theory? So this is actually at filling factor 3/7, it turns out. So the ground state will be described by 3 fill levels of composite fermions. So this is one unique state that you get. There is no degree of freedom that you have. Then the first excited branch of states you get by like a particle hole pair of composite fermions. And the degree of freedom that you have is where you place these composite fermion particles in holes, and that actually gives you this dispersion depending on how they are separated. And then these higher bands are all formed by taking higher and higher energies excitations of composite fermions. So this is the ground state, this is 1 particle hole pair, this is 2 particle hole pair, this is 3 particle hole pair, and so on. And this is the way you can build a whole spectrum and get statistical mechanics out of this, because you just create higher and higher excitations. Okay, so that's basically all I had to say. So I would like to end with one take-home message. So the point that you can take away from this talk is that If you have electrons in a magnetic field and strongly interacting with each other, they are extremely unhappy. Okay, so what they do is they let go of each other, grab hold of two flux quanta from the external magnetic field, and then they are free particles which are very happy. So on that note, let me stop and I'll be happy to take questions.
So we have time for a couple of questions.
So can you explain all the filling factors with this kind of a picture, or still there is some mystery left?
Okay, that's a great question. So you can't explain all the fractions with this kind of picture because of this thing that you can get only like odd denominator fractions of this kind. So if you get, there are even denominator states that are also absurd. For that you need to put in some interactions between composite fermions themselves. So that one can do. This is called the Jan sequence, yeah.
And can you get a fundamental theory out of it, like Chern-Simons theory?
You can write down a Chern-Simons field theory using this principle, yes.
So what is the zeroth order you talk about?
What is the zeroth order approximation?
Yeah.
Yeah, so the zeroth order approximation is to assume that these objects are non-interacting, because only for non-interacting objects you get Landau levels. So I neglect interactions between these particles. But as Sayantan pointed out, if you include interactions between them, then you can get something more exotic. But the zeroth order approximation is that these are non-interacting objects. So they form Landau levels.
How good they actually fit with the experimental data?
Yeah, so I don't have experimental results to show, but I have exact diagonalization results. So actually these dashed lines are obtained from brute force exact diagonalization. And this dot is obtained by this approximation, where in this approximation I've neglected interactions. So these dots essentially fit right over the line almost. So basically if I didn't tell you which were the dots and which were the lines, you won't be able to tell which is what. So it agrees extremely well with experiments also, but at least with theory it's very good.
If you work out the Hamiltonian,
Yeah.
given the wave function, that should be the ground state.
Yeah.
How far it is different from the wave of Hamiltonian?
So it's not very far. So if you look at the Coulomb Hamiltonian has this property that it's strongly repulsive at short distances. And if you look at, let's say, the Laughlin wave function, it's the exact ground state of a model Hamiltonian which has only the hardcore interaction put in. And also you can adiabatically connect from the hardcore interaction to the Coulomb. So topologically, all properties are the same. Microscopically, of course, they are slightly different.